In mathematics, structural stability is a fundamental property of a dynamical system, which means that the qualitative behavior of the trajectories is unaffected by small perturbations. Examples of such qualitative properties are numbers of fixed points and periodic orbits. Unlike Lyapunov stability, which considers perturbations of initial conditions for a fixed system, structural stability deals with perturbations of the system itself. Variants of this notion apply to systems of ordinary differential equations, vector fields on smooth manifolds, and flows generated by them. In diffeomorphisms, structurally stable systems were introduced by Alexander Andronov and Lev Pontryagin in 1937 under the name of systems grossiers, or rough systems. They announced a characterization of rough systems in the plane, the Andronov-Pontryagin criterion. In this case, structurally stable systems are typical. They form an open dense set in the space of all systems endowed with appropriate topology. In higher dimensions, this is no longer true, indicating that typical dynamics can be very complex. An important class of structurally stable systems in arbitrary dimensions is given by Anisov diffeomorphisms and flows. Definition: let G be an open domain in Rn with compact closure and smooth dimensional boundary. Consider the space X1 consisting of restrictions to G of C1 vector fields on Rn that are transversal to the boundary of G and inward-oriented. This space is endowed with the C1 metric in the usual fashion. A vector field Fx1 is weakly structurally stable if for any sufficiently small perturbation F1. The corresponding flows are topologically equivalent on G. There exists a homeomorphism H, GG, which transforms the oriented trajectories of F into the oriented trajectories of F1. If, moreover, for any epsilon greater than 0 the homeomorphism H may be chosen to be CO epsilon close to the identity map when F1 belongs to a suitable neighborhood of F depending on epsilon, then F is called structurally stable. These definitions extend in a straightforward way to the case of n-dimensional compact smooth manifolds with boundary. Andronov and Pontryagin originally considered the strong property. Analogous definitions can be given for diffeomorphisms in place of vector fields and flows. In this setting, the homeomorphism H must be a topological conjugacy. It is important to note that topological equivalence is realized with a loss of smoothness. The map H cannot, in general, be a diffeomorphism. Moreover, although topological equivalence respects the oriented trajectories, unlike topological conjugacy, it is not time-compatible. Thus the relevant notion of topological equivalence is a considerable weakening of the naive C1 conjugacy of vector fields. Without these restrictions, no continuous time system with fixed points or periodic orbits could have been structurally stable. Weakly structurally stable systems form an open set in X1, but it is unknown whether the same property holds in the strong case. Examples: structural stability of C1 vector fields on the unit disk D that are transversal to the boundary and on the two-sphere S2 has been determined in the foundational paper of Andronov and Pontryagin. According to the Andronov-Pontryagin criterion, such fields are structurally stable if and only if they have only finitely many singular points and periodic trajectories, which are all non-degenerate, and do not have saddle-to-saddle connections. Furthermore, the non-wandering set of the system is precisely the union of singular points and periodic orbits. In particular, structurally stable vector fields in two dimensions cannot have homoclinic trajectories, which could enormously complicate the dynamics, as discovered by Henri Poincaré. Structural stability of non-singular smooth vector fields on the torus can be investigated using the theory developed by Poincaré and Arnaud and Joy. Using the Poincare recurrence map, the question is reduced to determining structural stability of diffeomorphisms of the circle. As a consequence of the Denjoy theorem, an orientation-preserving C2 diffeomorphism f of the circle is structurally stable if and only if its rotation number is rational, ρ equals p, q, and the periodic trajectories, which all have period q, are non-degenerate. The Jacobian of Fq at the periodic points is different from 1, cf circle map. Dmitry Anosov discovered that hyperbolic automorphisms of the torus, such as the Arnold's cat map, are structurally stable. He then generalized this statement to a wider class of systems, which have since been called Anosov diffeomorphisms and Anosov flows. One celebrated example of Anosov flow is given by the geodesic flow on a surface of constant negative curvature, cf. Hadamard billiards. History and significance. Structural stability of the system provides a justification for applying the qualitative theory of dynamical systems to analysis of concrete physical systems. The idea of such qualitative analysis goes back to the work of Henri Poincare on the three-body problem in celestial mechanics. Around the same time, Alexander Lyapunov rigorously investigated stability of small perturbations of an individual system. In practice, the evolution law of the system is never known exactly, due to the presence of various small interactions. It is, therefore, crucial to know that basic features of the dynamics are the same for any small perturbation of the model system, whose evolution is governed by a certain known physical law. Qualitative analysis was further developed by George Birkhoff in the 1920s, but was first formalized with introduction of the concept of rough system by Andronov and Pontryagin in 1937. This was immediately applied to analysis of physical systems with oscillations by Andronov, Witt, and Kaikin. The term structural stability is due to Solomon Lefschetz, who oversaw translation of their monograph into English. Ideas of structural stability were taken up by Stephen Smale and his school in the 1960s in the context of hyperbolic dynamics. Earlier, Marston Morse and Hassler Whitney initiated and René Thom developed a parallel theory of stability for differentiable maps, which forms a key part of singularity theory. Thom envisaged applications of this theory to biological systems. Both Smale and Thom worked in direct contact with Mauricio Pisotto, who developed Pisotto's theorem in the late 1950s. When Smale started to develop the theory of hyperbolic dynamical systems, he hoped that structurally stable systems would be typical. This would have been consistent with the situation in low dimensions. Dimension 2 for flows and dimension 1 for diffeomorphisms. However, he soon found examples of vector fields on higher dimensional manifolds that cannot be made structurally stable by an arbitrarily small perturbation. This means that in higher dimensions, structurally stable systems are not dense. In addition, a structurally stable system may have transversal homoclinic trajectories of hyperbolic saddle closed orbits and infinitely many periodic orbits. Even though the phase space is compact, the closest higher dimensional analog of structurally stable systems considered by Andronov and Pontryagin is given by the Morse-Smale systems.